You ever rub your hands together to warm them up? Or think about what's really keeping a car's tires glued to the road. I mean, it seems so basic, right? Two things rubbing together. But the actual science behind friction, well, that's been one of the most stubborn, long-lasting puzzles in history. We're talking about a 500-year-old mystery. So let's just jump right in with this question. What on earth does Leonardo da Vinci have to do with the tires on your car? It sounds like a setup for a punchline, but it's not. The answer actually connects this Renaissance genius to the everyday physics that stops you from sliding off the road. Turns out Da Vinci was the very first person to stumble onto the secret of friction, a secret that, honestly, we're only just now getting our heads around. And this is the rule that's at the absolute heart of the mystery. It's called Amonton's law, and it is ridiculously simple. It just says that the friction force is equal to the load, the weight pressing the two surfaces together, times some constant number. That's it. And here's the really weird part. The law doesn't care how big the area of contact is or how fast the objects are sliding. And that just doesn't feel right, does it? And just look at this timeline. It's wild. For 500 years, from Da Vinci all the way up through the Enlightenment, we knew what happened. We could measure friction, we could write the formula, no problem. But explaining why it worked, why this simple little rule held up, it was a total black box, a complete mystery. Until technology finally got good enough to peek inside. And that right there is the question that has scientists totally stumped for centuries. I mean, if you look at any real-world surface under a microscope, it's not smooth. It's this jagged, chaotic landscape of peaks and valleys. So how in the world could a single, clean, elegant equation possibly describe what happens when you smash two of those messy landscapes together and drag them across each other? So the first serious attempt to explain this was, it was really intuitive. People pictured friction as a kind of microscopic mountain climbing expedition. The idea was pretty straightforward. The force of friction was just the effort it took to drag the little peaks on one surface, they called them asperities, up and over the little peaks on the other surface. It makes total sense, doesn't it? If you press down harder, the mountains get squished together more, and it takes more effort to climb them. But there was a fatal flaw. A scientist named John Leslie pointed it out way back in 1804. He said, hold on a second. Whatever energy you use to climb up one side of a microscopic mountain, well, you get all of that energy back when you slide down the other side. It's like coasting downhill on a bike. So if this theory were true, the net energy loss would be zero, which means there shouldn't be any friction at all. The theory just completely collapsed. All right, so with the mountain climbing idea out, the scientific investigation took a totally new direction. And this next idea was so good, so compelling, that it dominated the conversation for decades. But as it turns out, it was a fantastic red herring. So the next big theory, which came from two guys named Bowden and Tabor, was this. Forget the big, obvious area of contact you can see. Friction is all about the tiny, real area where just the very tips of those microscopic peaks are actually touching and basically welding themselves together. Now, the logic here seemed solid. You push down harder, right? That squashes the peaks, which increases the real area of contact. And since friction is just the force you need to break all those tiny welds, it makes sense that friction would be proportional to the real area, which is proportional to the load. Problem solved. Except it wasn't. Other parts of physics, really well-established theories, predicted by the real contact area doesn't grow in a nice straight line with the load. It grows in a curve. The new theory just didn't line up with the rest of physics. The math didn't work. So this real area of contact idea was a huge step for sure. It got us thinking in the right way. But it just wasn't the fundamental answer to why a mountain's simple law worked so well. It was a major clue, but it wasn't the solution. The case, once again, went cold. For this case to finally get cracked, we needed new tools. We needed a way to actually see and measure what was happening at those tiny points of contact, at a scale millions of times smaller than a human hair. We needed to get down to the nanoscale. And this is where modern tech really enters the story. Things like the atomic force microscope and the surface forces apparatus. These incredible machines finally let scientists act like real forensic investigators, measuring both the friction force and the real contact area at the exact same time with mind-boggling precision. Okay, get ready because this slide is the smoking gun. This is real data from one of those experiments. Look at the open circles. That's friction versus load. It's a perfect, beautiful straight line, exactly like Omenton's law said it would be. But now look at the filled circles. That's the real contact area versus the load. See that? It's a curve. They do not match.
The conclusion was just inescapable. The experiment proved beyond any doubt that friction follows the load, not the real contact area. The real area theory, the one that had dominated for decades, was officially busted. The real cause of friction was still out there.
And so the final breakthrough, the thing that finally solved the case, didn't come from looking through a microscope. It came from a supercomputer. These unbelievably powerful molecular dynamic simulations finally let us watch the invisible dance of molecules that actually creates friction. So what did they see? What is actually happening down there when two rough surfaces, maybe with a little bit of lubricant trapped in between, slide past each other? Well, this slide shows it perfectly. If you have perfectly flat surfaces, the lubricant molecules can line up in these neat, orderly layers. But look at the top image. On real-world, rough surfaces, it's a completely different story. The molecules are just stuck in there in a totally disordered, chaotic jumble. And this is it. This is the real mechanism that burns off energy as friction. As those surfaces slide, individual molecules get trapped for a split second between approaching peaks. They get squeezed hard, and then they get released. It's happening over and over and over again. Billions of tiny, irreversible squishing events all at once. And here's the thing. If you could zoom in on just one of those molecules, the process would look anything but simple. It would be totally chaotic. The forces are complex. They don't follow any easy rule. It almost seems like the mystery is getting deeper, not simpler. But then, the simulation shows us the magic. When you zoom back out and you average together the forces from billions and billions of these chaotic, messy molecular squishes, something incredible happens. A perfectly simple, straight-line relationship emerges from all that noise. And that straight line, that is a Montan's law. There's actually a name for this phenomenon in science. It's called an emergent property. Think about it like this. A single molecule of H2O isn't wet, right? But billions of them together are. A single neuron in your brain doesn't think, but your brain does. It's the same idea. A single molecular interaction isn't simple and linear, but the collective result, friction, is. So in the end, that simple, beautiful rule that Leonardo da Vinci first sketched in his notebook 500 years ago, it isn't the result of some simple, elegant mechanism. It's actually the statistical average, like a ghost, of an unimaginably complex and chaotic dance happening at the molecular scale. It really makes you wonder, doesn't it? If something as ordinary and everyday as friction is built on this foundation of hidden complexity, what other simple rules we take for granted in our lives are just the beautiful, orderly surface of a deeply chaotic world we never even see?